Team Gary, welcome, and we're doing science in the AM. Here we are, Delca. Yesterday, we were playing around, and I just said, figure it out. Light up 2 light bulbs. This is the method we came up with. There's another one. We'll play around with that later. But right now, you guys are at least set up, right? Something like this. If you need extra wires, you know where they are. We did use something, the setting where we call it an ammeter. That measures the current. Okay? We measured the current in 3 different spots. When we measured it between the positive end of the battery and the first bulb, we got more or less the same reading in between the bulbs and between the negative end of the battery and the bulb. And I was saying, this makes sense. And there's reasons why you might consider to loop this, this way or this way. But let's talk about electrons. This is not the way you'd see it if you were actually studying electricity as an electrician. But it works either way. Negative electrons are zipping out that way. They're passing their charge along. So does it make sense? I was saying the analogy of water, we understand. If there's a hose, and it's going by here, 18 liters in 1 minute, wouldn't you expect then 18 liters to be here every minute, and then 18 liters here every minute, and then return back to the pump? Maybe it's a lazy river or something. This is why I had the meters, but now, in a series circuit, I had to write this down. We're now going to take a look at the voltage and the way voltage is measured, and we can use the old meters so that we actually could have more voltage, but we don't have to realize it. We have more voltmeters. What we're going to do is take the voltmeter, and you're going to, where I have blue lines, that means I'm going to get you to measure across the battery, the blue lines here. The volt equals, actually the voltage is the unit. We say the potential draw equals. But you're going to measure it at the battery just while it's hitched up. You might have 2 batteries because that's what you need. One group won't have 2 batteries and keep blowing up. Too much juice. Right. Okay, anyways, you're going to measure it while it's on, across there, a needle on each end, right? Then you're going to measure it here, voltage equals. Then you're going to measure it across here, the voltage equals. So is everybody clear on where they need to measure this? Because remember what voltage is, and I said it's like a potential energy, really. It's the energy of the electron. The idea is that when you use energy, it drops, or I mean, when you have a circuit, the energy in the electrons drops across when it's being used. And we're going to see how much it drops across each of the 2 light bulbs. And across the battery, see how much it increases. So that's the 3 measurements you're going to do here. Okay? I'll get you guys to do that in the next minute. I'm going to pause the video. And actually, luckily, I'm going to this, so it shouldn't be that many. I'll give you guys time. I'm going to just go over some measurements. Hey, you need paper, I have some up here. But I saw some good stuff going on. Here's what I need. I'm going to only go over one group's measurements, but we're going to see if other groups were like this. Yes? Okay, we'll put that on hold for the moment. So, with the group that I work with, is it 2.6, okay? We measured, oh, it's swirling on me, 2.6 volts. We measured 0.5 volts here. What was the other one? 2.2? Now, I'm going to ask you something. Those needles aren't the most accurate, right? Like they flutter a bit, and you're kind of guessing. Did you guys, I'm going to ask frankly, because you guys are good, and then maybe check in with some others. What did you guys get at the battle? 2.4. What'd you get for this and this? Yeah. The biggest voltage came from here. Cameron, what'd you guys get? For the battery? 0.1? 75. Okay, 0.75. That's a big one. What'd you guys get here and here? You may approximately add up to the grand total of the battery, the two volts. And this is within round. This one doesn't exactly. 2.2 plus 0.5 is 2.7, but it's very close. How about you guys? Does it approximately add to the grand total of the battery? It doesn't sound like everything. And that sometimes happens. Okay. Now, what it is that it really should, in theory, add up perfectly. These meters aren't the most accurate. Sometimes there's weird energy loss through the wires themselves. You know how sometimes with the copper wire, when it's bare, you can feel it. There's energy being used, just the friction in the wires, okay? But in this series circuit, that actually. What in theory should happen, and I saw it very close to the decimal one, the individual voltages across the batteries add up to the total voltage across the batteries. The individual voltages, those ones across the bulbs, add up to the voltage across the battery. Now, we're going to think of something here. While you jot that small sentence down, it won't take long. Within reason, within a decimal or two, that's what you found. Now, I'm going to get you to draw an analogy. When I say analogy, you guys, what's an analogy in English? You know, reading the story. What's a simile if I say this in English? Simile. That's a comparison where you use like or as. Pretty as a rose or something like that. Well, an analogy is usually more complex, but it's, maybe you guys like poetry, some people hate it. But you can use an analogy to compare one situation to another situation, and often and I'm not going to get into English analogies too much, but it's a word I think you might have heard, and if not, you're going to pay attention here because you're in English, where you use one thing to compare another situation. Anyways, I'm not going to get into it too much. We are going to, just like our analogy with water, we're going to use an analogy here with the batteries and the electrons and the energy. The water is one analogy, and we could think of this as a waterfall, or we could think of this, I like thinking of it as a, when you were in elementary school, play structure. I'm going to put in, here's my analogy. Here's my battery, right? My negative and my positive. The measurements I used from Mesmeret and Elise group was that 2.6 volts. And I put the battery, what you might think of as upside down. Why? Because the negative end actually scoots out the electron. And this totally works if you follow it from the positive. It doesn't matter to me. As long as you realize the electrons are the things with you. The reason why it doesn't matter is that if you study electricity as an electrician, you might follow it from the positive, and it still gets you the same. So this is like a really awesome play structure. It's more like a ski hill where you get pulled up the mountain or whatever, right? So this is like the stairs. You use some energy though on the play structure. Maybe you had an elevator, I got it. So you get boosted up here. And then on the plate structure, you're at this level here. We're going to say you're 2.6 meters high. That's actually, this is 2 meters, right? So about the height of the ceiling. So it's a good size plate structure, right? Okay. You're at 2.6 meters from ground level instead of volts. That's the electrons. Then you have a choice, or not a choice, but you're going to take one slide down. And the one slide is 2.2 meters. So I'm going to go longer. 2.2 volts you dropped. How much left to get back down to ground level? Okay, yeah. We use 0.5 because that's what it's as accurate as our measurements were. You get to this level, and then there's a little kiddie slide, right? Half a meter is about a little better than knee high for me, right? You know what I'm saying. Then you got this one little jump slide down. You're at ground level again. This is the 0.4. Now, this is the circuit. And I want you to put this analogy kind of thing. This is how we can understand the circuit. Like think of it as like a gym, play structure, right? Or a ski hill system. Not everybody's familiar with ski hills though. But it's the same kind of thing. You take the ski lift up to the top of the mountain. The first run you do, come down most of the mountain. You still have some more potential energy. And you scoot over sideways and then you drop down that little last bit. Or a system of slides in the place. Does that make sense? Okay. Then you run back to the ski lift or to the stairs for the play structure. You re-energize, you get more potential energy, and you come through again and again. And that's why the light bulbs are constantly lit up. It goes round and round forever. It's a circle, it's a loop. That makes some sense. Now, I want, at the same time, how about, did anybody try this? Have your bulbs lit up. You don't need meters. At least a couple of groups, anyway. I want to ask you something. Have your bulbs lit up. Okay. Another person unscrew one of the bulbs. Okay, what happens to the other bulb when you unscrew it? Screw it back in and it'll turn on, right? Okay. Brother and sister, get along. Okay. Okay. So, in a series circuit, does it make sense if I'll get your attention again. I know, actually, you're trying something I asked you to, so that's, I'll give you the 30 seconds. Try it out. Okay, I'll get your attention again. Pardon me. So what we had is that if this bulb here is disconnected or it burns out, the other bulb won't work even though it's a good bulb. Does this make sense? Let's see here. This would be, try to get your attention. This is why. Oh, does it make sense? Okay. Gets to here, and this bulb, let's say, is unscrewed or burnt out. It can't get past, it can't flow past that bulb to get to the other one. Does that make sense? Why? Now here's my question. This is called a series circuit. In my house, there's more than one item on an electrical circuit. You know about blowing breakers in your house? Okay. Sometimes if you have the microwave on at the same time as another food processor or something like this, it'll flip a breaker or something like that. But there's about sometimes there's only 1 or 2 items on a circuit. Sometimes there's 10 items. I think you can have up to 12, I think. I'm not electrical code, so I won't tell you that for sure. If a bulb burns out in your house, does it shut off all, like just a light bulb, just burnt out? Does it shut off all the other lights in your house? No. So that tells me this is not the way my house is wired. However, with Christmas lights, if you celebrate Christmas and put up Christmas lights, do you guys know what happens sometimes with one bulb? Does it burn out the whole house? Some brands do. It depends on the type of lights. There are some things, but they're actually not that common because you have a problem with one thing. You don't want everything else not working, right? So there's got to be another way to wire up these bulbs. Has anybody dreamt this up yet? Has anybody dreamt up another way to wire two bulbs that's not one after the other, so that if one burns out, the other one still can be lit up? Huh. Okay, don't worry about this. Why don't you do, well, we'll drop these down before we get to the other one. Okay. What is a series circuit? I think when we have, how did we explain it on the other page? I want to just double check because I don't need to repeat. This is called a series circuit. In series means one after another. When you have one bulb after the other, you have a series circuit. You can pitch up 10 bulbs, 5 bulbs, whatever. Right? You just do because you keep burning them up. Okay. And jot this down first. Then we'll talk about the next part. It's called parallels. By the way, too, when it comes to testing for this unit, part of my test will be calling you guys up and doing one-on-one kind of, I'm going to ask you, can you light up this bulb? Can you light up 2 bulbs in series? Can you light up 2 bulbs in what we're going to learn about parallel? And some of it will be written tests too, but some of it will be performance, sort of like in, you're doing a unit in phys ed, you might have some skill tests too, right? Part of us is not all book work. I want to get you guys to do some hands-on work, so it's important to pay attention how to wire things out. Okay, to reiterate what you have just written down, or I see some are still writing. You have one bulb after another, you have a series. Just like a TV series is one episode after another. Binge watching a series, right? One after another. You don't go out of order. You want to. Now, the next statement, a series circuit has more than one resistor, and that's anything that uses electricity to do work. These old school bulbs light up because there's a resistance to the electron field. It gets its name from having only one path for the charges. Okay, Shidaka, we're sick of this. Let's get another way to wire up bulbs. Clearly, this is not how it's done in the house. That's what we're thinking. One bulb burns out, the other ones are still on. Okay, we're going to see what this parallel business is. Pause one. I'm giving you the diagram for a parallel circuit. Don't worry about the numbers right now. I'll talk about that later. But parallel circuits, in a parallel circuit, do you see how this works? You should understand this before you write it down. Really, it's like lighting up one light bulb, and then this wire and this wire here, you have a second loop. There, right? And then you can extend that to 5 of those light bulbs or whatever. This is how the plugins in your house are wired, actually. It's neater and tidier, like the wires don't go in circles, literally. But I want you to draw this first, and then draw the other light bulb, like that, okay? You're drawing this right now. And then you're going to wire it up and see how this works. And you're going to see, and I already have this thing, in a parallel circuit, the light bulbs do not get dimmer when you add more lights. You know how one was dimmer than the other? And they definitely were dimmer than it was just one lit up. And there's a reason. I'm going to talk about the numbers before we get this wired up. Then we're going to put in, I put the amps in. So the diagram, maybe write down the 80 milliamps, the 200 milliamps, and the 120 milliamps. Those are measurements from the other year, but since you don't have a lot of the ammeters, I I'll get you guys to just take my word for this. Okay? We'll measure the voltage. So let's see something. You got this down? Yeah. You got the numbers down too? Now I said do worry about the numbers now. So they're amps, that's the current. Yeah, I'm going to start recording now and mention some things. So I need your attention again. Some of you are still writing it down, that's fine. I'll get you to watch this because I'm going to make sense out of these current numbers. I'm going to use the water analogy idea first. Right here, this battery is boosting the electrons, and I know I got it the positive end at the top, but we'll talk like this, okay? The electrons come out, and they are whizzing by 200 liters every minute, let's say. This is a big. The 200 liters are coming out, and then they get to this point here, a junction. Each water molecule can only go one path. It can't go two. So either the water drops go this way or they go this way at this point, right? Well, if 120 of these 200 go through this light bulb, how many are left go this way? 80, right? 120 plus 80 makes 200. 200 came out. 120 of them went this way, so that means 80 of them had to go this way. You kind of follow the logic there? 80 liters of water went this way. 80 liters of water, return and join the other 120 liters of water to make 200 in the end, and they go back to the water. Well, the battery is the pump, right? Does that make sense why the current works the way it does? What I want you to do, and I think you might suspect this, the bulbs don't get dimmer. So if you measure the voltage here and here, measure the voltage at this light bulb, here across that, and then measure the potential drop, the voltage, across that light bulb. One person gets that circuit going, and I want to hear the kind of numbers you get for voltage at those three spots, okay? That's what we're doing in the next, well, we've got 9 minutes and then we're out of here, so let's hurry. I'm going to run through some things. I worked with one group, and I know their results, and it's exactly as expected. What do you guys get? You blew up every bulb.
No, you're fine. And we also added a third light bulb.
Okay.
And two of them out of the three.
Okay. That doesn't surprise me. Okay. This is why we use both batteries so nobody gets hurt. Okay. I'm going to talk about voltage real quick, guys, because we don't actually have much time. 3 minutes of it. Not cool. Okay. Can I? How about middle table? Did you guys get some voltages? Measure? Right? Your table? What did you guys get at the battery? The voltage. No? Okay. What did you guys get for voltage? 2 for everything. They got what we used. It depends how many batteries you use. We got 1 volt, 1 volt, 1 volt. You guys got 2 volts, 2 volts, 2 volts. Now, I'll just go with the 2. It doesn't matter. But the idea is that 2 volts across here, 2 volts across here, 2 volts across here. If you had 1 volt, 1 volt, or 1.5 volts, that's fine. The voltage is the same. Does that make sense? Why the bulbs are not dimmer? It's not being shared. The current is being shared, but the voltage isn't. And that's a good thing in a house. That means if I plug in 5 items, the voltage doesn't go down. This is why we want our house measured in parallel. I'm going to pause the video recording, and we'll tidy up things at the end, and I will address your concerns in a second.